Thank you everyone for being here. I can see in the audience so many colleagues, so many friends, even childhood friends that I haven't seen for 20 years. I know you're there. Thank you for joining. And it is my actually third time on this stage giving a talk, and I realized that for the third time again, I will be giving a talk about AI. And I have the feeling that over the past 3 years, I've been talking only about AI with professionals, colleagues, friends, the members of the localization think tank, which we founded a year ago. My colleagues here at RWS is just AI, AI, AI. And everyone agrees that AI is here to stay, but everyone also is worried a bit about what AI will bring, because sometimes it feels scary. As Anna mentioned, things are happening at a crazy pace, and it really feels like the world around us is spinning at an incredible speed. Things are changing so fast. We don't know how to predict. We don't know how to prepare. And that is not an illusion, because indeed, innovation accelerates exponentially. The world is getting faster, and this is best visible actually in the world of technological innovation. This is driven, by the way, by the so-called law of accelerating returns. So basically, it states that the rate of change in any evolving system, such as technology, increases exponentially and not linearly, but that is too academic. I'm actually often accused of being too academic. So let me show you for a 10-year-old what this looks like and feels like, not in such academic terms. And for that, I was inspired by the brilliant George Land, who had this original idea to compress the history of human innovation into a single calendar year. And this is the story that emerges then. So the year begins on January 1st as the clock strikes midnight with the invention of the very first stone tools. And then for months, nothing happens. Nothing. The calendar pages turn. We have March. Humanity is still using stone tools. Then comes February, March, stone tools. April, stone tools. May, still we are using stone tools. June, stone tools. July, stone tools. And it's only in the middle of August that our early ancestors finally gained control over fire. Think about that. Over 7 months of our historical year has passed before this breakthrough. But actually the world, as we know it, has been built in the last 2 days of this calendar year. On December 30th, in the morning, the agricultural revolution dawned. And then the whole day, nothing else happened, nothing else. It is in the early morning of the next day that we invented the wheel. And everything that we call recorded history actually happened in the last 24 hours. So later, after sunrise, we invented writing. Then the Iron Age started like in the afternoon around 3 p.m. Then in the evening, the pace became a bit faster. The first Roman aqueducts were built shortly after sunset. Gunpowder was discovered around 9:30 in the evening. Then we approached 10 p.m. and we invented the mechanical clock so that we could tell the time even when the sun doesn't shine. And then a little bit after 11 p.m., we discovered electricity so that we can also work when the sun doesn't shine. And then came the Industrial Revolution powered by the steam engine after 11 o'clock p.m. So it's just like less than an hour until the calendar year ends. And then we approach 11:30. We invent the telephone. Then we invent the automobile. Then 23:36, we invent the airplanes, and then 1:45 we invent the computer, and then a couple of minutes later we send a person to the moon, and then it gets even faster. Then 23:52 we invent the internet. It starts spreading first slowly, then faster, and then comes the smartphone 2 minutes before midnight, and then just before the clock strikes again, a very clever team at Google in 2017 invent the transformer technology, and the new year starts. And I would say not just a new year, but a whole new era, because AI is a very, very different innovation from all innovations that preceded. Because until that point, Every human invention could be explained in the tiniest detail by the inventor, right? James Watt could explain precisely how the steam engine worked. Alexander Graham Bell could describe the telephone in the tiniest detail and explain exactly how it works. Their creations were deterministic. If you understood the mechanism, you understood the outcome and you could predict it. But AI is different, because the AI creators cannot fully explain why a particular output appears. We understand the architecture, right? We understand the training process, but we cannot trace every decision an AI model makes. So for the first time in history, humanity has built an innovation that we ourselves cannot explain. And we have to create whole new branches of science to understand it. We now have AI neuroscience. We have AI interpretability research. We are peeking under the hood of our own creation to understand how it works. And this is big because we study AI models using the same technology, the same tools in which we use to study the human brain. That's why this innovation is so much different from everything else that we did before. That's why it also feels a bit scary, and it's so big and it's so complex. You know, these are giant models. They almost feel intimidating. They have those billions of parameters. You know, the frontier models have even up to 1 trillion of parameters. They are trained on those incredibly massive data set, all of the internet. It takes a human 170,000 years to read all of that. They cost a lot. Training a frontier model can cost up to $500 billion. Bringing up a child in Europe actually costs less than $500,000, college included. So all the training is already included there, yeah. And they consume these immense amounts of electricity. And while our brain is so much more efficient, right? We run on 20 watts hour. Yeah, and because we are so much more efficient, we need much less to get trained. And if you remember my talk in 2024, I showed you there how little my little daughter Emma needed to actually learn language, unlike a large language model. So at the age of 1 year, she had been exposed to just 1 million words, and she could already babble. And at 3 years, after being exposed to just 30 million words, she could already tell stories. And at the age of 5, with just 50 million words, she was already reading. So honestly, I think that's the reason this was the most watched talk in 2024, because it had a cute baby. So let's continue the trend and see, where is Emma today? So today, Emma is 8 years old. By now, she has been exposed to over 85 million words minimum. She's reading 500 pages a week, so she gets more through the books. We talk to her in many different languages. She already has 4 languages in her linguistic repertoire, and she wants to study more languages. And to support her learning those languages, every evening we lie in bed and we read 2 books. One book is in my language, her mother's language, different from the language of her environment. And the second book that we read is Greek mythology in English. English is a second language for her. And in order to make sure that she has understood the content, I read for her an English sentence, and then I ask her to translate it, because translation is actually the best way to test whether a person understands the content. And in the beginning, she was translating from English word by word, right? So she would just translate the words, and the result could be slightly ungrammatical. And then gradually she started producing grammatical sentences in the target language. She was still closely following the source. And a few months ago, something really interesting happened. When I asked her to translate, she would pause much longer than before. And then her hands would start moving, but she'll be silent. She would be just drawing these invisible shapes in the air. And then after a while, she would say a translation that was not word by word. It was a translation that perfectly captured the meaning of the source and the feeling of the source. She would add something, she would remove, she would be looking for the perfect way to render the same meaning and the same feeling in a way that sounds natural. So her hands were dancing and she was dancing with the words. And that's when I realized, well, my little Emma has now become a real translator, like all of you here. And that was a wonderful moment, almost like seeing the first tooth or looking at the first steps taken by a baby starting walking. So Emma, as you know, she's the one doing all the pictures and drawings for my presentation. She's always next to me. Also for this presentation, we were preparing it together. But a while ago, while she was doing some drawings for another presentation, I had the famous Asterix and Obelix sitting at my desk. She suddenly turned to me and asked me, Mom, now that I'm a translator, do I translate as well as an AI model? And then I told her, much better, my dear, because unlike an AI model, you actually feel what you say and you choose your words differently and your hands dance when you search for the right words. And then she asks me, but why do my hands have to dance when I translate? And then I had to explain to her what all happens in her head when she translates. And I'll tell you too. Let's start from the very, very basic. The basics are our brain. This is our brain. This is our biological neural network. We have about 1 billion neurons, those cells, and they make up the gray matter. And in addition to that, we also have the connections between those neurons called axons. These are like many tiny threads between all the neural cells, and those make up the white matter, right? So our brain is a lot of gray matter and actually a lot of white matter as well, which matters just as much as the gray matter, right? So we have lots of neurons and extensive connections between those neurons. What happens in the brain of a translator? Well, when a translator hears a sentence or reads a sentence, the whole translation journey begins in this area called the Wernicke area. This is where the understanding of the source text happens. It's very close to the visual cortex, which is right behind the head. That's where, for example, the information about written text comes in and goes to the Wernicke's area. And it's also very close to the auditory cortex, so that when we listen and we consume language through sound, also there is not a very long way to the Wernicke areas from there. So source text comes in there, and in the Wernicke area, our brain processes the understanding of the text. What is the underlying meaning? What is the context? What is the intent? And for that, it is helped by the long-term memory. And there are two types of long-term memory. The first one is semantic long-term memory, which is basically our storehouse of general world knowledge. This is where we store all the facts about the world, all the concepts. This is also our dictionary. This is where we store the meaning of words. It is our encyclopedia and our dictionary, and it helps the Wernicke area understand the literal meaning of a text. So we need the Wernicke area and the semantic memory, which is the memory of what things are. But then there is another kind of memory, which is also long-term memory, and this is episodic memory. This is where we store our personal experiences together with our emotions, our sensory details tied to them, how things smelled, how they felt when we touched them. This is the memory not of what things are, but the memory of how things feel. This is if the semantic memory is our encyclopedia, then the episodic memory would be our personal diary. And this is a very important memory for a translator, because in order for a translator to grasp a cultural intent or emotional nuances or humor even, they need to draw on this episodic memory to understand those subtleness in the source text. For example, a translator from, say, English or Japanese to English or English to Japanese, who has lived in Japan and now needs to translate a particular dialogue, this translator can draw on the episodic memories from the stay in Japan and choose the right, like have a feel of this situation and choose the right level of formality for a conversation, drawing on the social context where the translator encountered similar levels of formality and choose the right translation. And that's a skill that goes beyond just book knowledge. It is a skill that it is a feeling that the translator acquired through his or her experience. Okay, so this is where we process the source text, but then we need more. Once we have understood the meaning, this information from the Wernicke's area is passed to another very famous language area in the brain, and that is the Broca area. Broca area is in the frontal lobe, and this area plays the main role in producing the target language. So this is where we construct the language, right? We hear this where our brain builds the correct syntactic structures of the target text and basically produces the target text. And those two areas are connected by something. It's a neural pathway which is called arcuate fasciculus. Okay, that's the hardest word I'm going to use today. Promise won't get worse than that. And it is basically a bundle of nerves that transfer the information from the Wernicke's area to the Broca's area. Okay, this is crucial for translation because you need to pass information from the source area to the target area, right? From understanding the text to where the new text can be created. Without the arcuate fasciculus, there's no translation. In fact, people who have a damage to the arcuate fasciculus because of a stroke or an injury, they have a very interesting condition called conduction aphasia, which is that when they hear a sentence, they understand it, but they cannot repeat it. They simply cannot repeat it because there is no connection between the Wernicke's area and the Broca's area. Okay, but that is not enough. Translation is a super cognitively demanding task, and it requires much more than these two areas. So we need to engage a much broader network of executive control to manage this cognitive load. For example, we have something called, this is called ACC. Let's call it ACC, part of our brain, which monitors for conflict. So this is a part of the brain that can detect ambiguous words or false friends. For example, the word gift, which in English means a present and in German means a poison, right? Or for a Spanish English translator, this area lights up very brightly whenever they hear the word embarrassed, which in Spanish means pregnant. It's a false friend. So this area is monitoring for conflicts, for ambiguities, for kind of places where errors can happen, and it sends a signal. Once it detects such a word, it sends a signal to the dorsolateral prefrontal cortex. Okay, this one is the attention manager in the brain. So once it receives a signal from the ACC saying, here is a word where you need to pay a lot of attention because there's a high risk for confusion and error, it actually allocates attentional resources in the brain to those words to resolve the ambiguity, to repair errors, and so on. Right, so the first one flags attention, that attention is needed because of ambiguity. The second one is allocated that attention. And we have more brain areas engaged. For example, in the basal ganglia, we control for language. That's the inhibition center. People who have it damaged usually have Parkinson's disease, right? This is actually one of the root causes for Parkinson's disease, right? This area has to now make sure that the two languages that we work with are separate, so that we do not, that there is no spillover from the source language into the target language. So it actually has to inhibit the source language so that the Broca area can produce a translation in the target language only without influence from the source language. It also helps with selecting the right words and the grammatical structures. And of course, we use a lot of our working memory, which is distributed all over our brain. It's not a single area, because all the time we need to remember the source meaning. We need to know what we are translating. We need to remember the potential word candidates that we have found and compare them to find the best one, and so on and so forth. As you can see, it's a very cognitively demanding work, extraordinary feat, intellectual feat. And then when all of this is done and you don't even notice that you do it, one of the attendees here, a friend of mine, Johan, he said, I have no anterior and singular cortex explosion at all. When he looked at my slides, he said, I just translate. Well, just translate means much more than just translate. So once we are done with that, then our Broca area actually produces the target translation, which means that it organizes the words into a grammatically correct syntactic structure. It ensures that all the words have the correct morphological encoding, the correct tense, the agreements, the plurals. It builds an entire phonological plan, which then says to the mouth and the tongue and the larynx and the pharynx how they should move in order to produce the language, or it tells the hands how they should move in order to write down the translation or type it. And it's also in parts, it basically also programs the gestures and all the stuff that accompanies language production. So as you can see, translation not only activates like some core language areas, in fact, it heavily relies on many other high-level cognitive functions in the brain. This is the reason why if anyone can multitask, then these are the translators. If you're a translator, you have such an excellent executive control and you know how to inhibit noise that you are very resistant to distractions and can multitask better than non-translators. Even better, if you're a translator, you can multitask even better than simply bilingual people, right? So translation is very good if you need to cook and call and write emails and translate on the side, but it's also very good for your mental health because it's a real mental gym. In fact, there is a lot of research which shows that the brain of translators is different. They have more gray matter. Those are the neurons. They have denser brain cell structure networks in the language areas and in those executive control centers. So they can actually process information faster. Yeah, you guys, you process information faster. Not only that, the connections between those areas are stronger. Translators have more white matter pathways, more efficient, more dense, more robust white matter pathways. These are the connections between the neurons. This is your white matter. And because of that, on MRI scans and in research, neuroscientific research, people have seen that actually the brain regions of translators communicate faster. And all of that builds something that is called cognitive reserve. And this is the brain's ability to cope with challenges, from the environment or, simply aging, and it postpones the onset of age-related cognitive decline. So if you are bilingual, and especially if you are a translator, the onset of diseases such as Alzheimer and senile dementia is offset by at least a decade. So if lifting weights is bodybuilding, I think we can agree that translating is literally brain building, and it's good for your health. So there's one more thing that is very important during translation, and that is that our brains don't just process words as symbols, they actually simulate what they process. They really simulate sensory, motor, emotional experiences. For instance, again, on MRI scan, what people saw is that when we see the word kick, this actually activates the motor system in our brain that makes a leg move in order to kick. We don't kick visibly because we have inhibition, but our brain sends a signal to our leg to kick. And similarly, when we see things like push, the motor area that is responsible for our hands coming up and pushing gets activated. Now, because of inhibition, again, we don't move visibly, but this twitching, this micro movement, the brain reacts as if the brain is really sending a command to the hands to push. Similarly with smile, again, the same neural activity in the brain. And this is not only with motion. The same thing happens for the sensory system. So if you see a word which describes some sensory experience, for example, velvet, the same sensory cortex activates as when you touch velvet. Similarly for frozen. And if you see cinnamon, you may even feel the smell. because your olfactory cortex activates. Olfactory means related to smell, right? Similarly, with emotions, emotionally charged language also activates brain regions that are involved in experiencing those very same emotions, right? You see joy, your dopamine goes a little bit up. You see grief, your cortisol goes a little bit up. And this is the emotional resonance that we experience when we read language. This is the emotional weight of language, and this is what a translator feels. So when a translator reads a text, the brain behaves as if the translator performs the action, experiences the feelings, and has the same emotions literally in the brain. And this is what makes a human translator a good translator. Okay, but now I was answering the question of Emma, why does she move her hands? Okay, at this point, I believe I managed to explain what happens in a translator's brain when translating, but I left the hands unexplained. And let me give you just a quick explanation. So as you already saw, I indicated it already, gesture and language are actually not two separate systems, but they are part of the same system of communication. We always move our hands when we talk. Even when we talk on the phone and no one sees us, we move our hands. Blind people gesture, even though when they talk, even though they've never seen anyone move their hands simply because they're congenitally blind. Even more interesting, if there's been very interesting research done on people tying the hands of subjects who talk. And then if you tie the hands of a person who talks, that person will start moving her head. And if you really manage to immobilize the person to not move while talking, then you know what happens? Speech fluency decreases. Speaking is not performed at the same level. So we need to move when we talk because gestures are actually part of the language production process. There are two important things, ways in which moving your hands helps you be more fluent. First of all, micro movements, these gestures, they help retrieve the right words. They really help us literally find the best words because it's shown that gestures help the speakers access the words from their mental dictionary. That's why when you tie a person's hands, then speech fluency decreases. And the second thing is that gestures reduce the cognitive load. As you saw, translation is not I just translate. It's actually a lot of stuff happening in your brain. And by moving, the gestures reduce this. It's a kind of a cognitive offloading. So hand movements, gestures, and language are interconnected. And it's there, of course, connected in the brain. Because if you remember, when I said that the Broca area produces language, I told you that it produces syntactic structure, morphology, articulatory plan, how to move our lips and tongue and so on, but also fine motoric gestures. The Broca area is involved in planning fine motoric movements. Okay, so it controls not only the mouth, the lips, and the tongue, it also controls the hands. And you can see that this connection goes both ways, because when we do something very complex with our hands, especially you can see it in young children, we also move our mouth. Yes, we move our mouth and we move our tongue. So this is, I watched Emma once do that. Let me play you this video. Watch it carefully. This is Emma learning to saw. Okay, look at her tongue. You see how she's moving her little hands and the tongue is coming out. That is basically the Broca area at work. And now I'm pretty sure that those of you who watched her carefully, something happened in your brain. The very same neural circuits that made Emma stick out her tongue activated in you as well. And about 30% of you actually moved your mouth. I was watching Anna to see whether she did. She did. And 10% of you probably even stuck out your tongue a little bit. Because when we see somebody stick out their tongue, our motor cortex activates for us to stick out our tongue as well. This is the so-called mirror neuron system. So when we see an action, it activates our action system. When we read about an action, it activates our own action system. When we hear somebody speak about an action, it activates our action system. When we hear somebody speak about an emotion, it activates the exact same part of our emotional system. And this is the core of this main idea behind language and translation, which is called embodied cognition. Language is not an abstract symbolic system. It's not processed as an abstract symbolic system. It is felt. It is literally felt by the reaction of your brain to it. So it is grounded in the sensory and motor systems that we have. And this grounding in the real world, in the real feelings, in the real perception, like in the way we feel like we really kick when we read about kicking. And this embodied cognition is at the base of human translation. So our understanding of language is not abstract. It's rooted in our physical and social and emotional experience. It is grounded. So understanding a language is actually feeling a language. And translation at its deepest level is precisely the art of transferring this embodied simulation across languages. And that's where the creativity of translation comes from. It comes from the translator's ability to understand not just the kind of literal meaning hiding behind the words, but the tone, the emotion, the cultural nuances, the intended impacts. That's where the embodied cognition is so important. It helps us when we understand metaphors, for example. Metaphors are very often rooted in purely physical experience. So we say things like, I have a heavy heart, okay, or the burden of life, right? So this literally weighs you down. Your brain reacts as if you are exposed to some weight, okay? Emotions are also deeply tied to our physical bodies, right? So a translator reading a text, a dialogue really has her experience of joy, sadness, anger, and these feelings that get truly evoked just need to be conferred, to be further passed on through language. Same with culture, right? The translator's lived experience within a culture provides this intuitive understanding that allows the translator to produce a translation that feels natural, that feels resonant, and so on. In short, creativity in translation comes from this ability to really feel, but I mean really feel on your body the source text on such an experiential level that you can just reconstruct the experience by choosing the right words and recreate the same experience. So that's humans. But then, of course, once I explained that to Emma, she asked me, okay, that's how I choose my words, and now I know why I move my hands. But how do LLMs choose their words then? Oh, and that is totally different. And I think those of you who've watched my presentations know what's coming now. A lot of math, a lot of math. So let's try that. But now that I convinced you all how complex things your brains can do, I'm pretty sure that math is going to look easy for you. Okay, so let me just remind you, you've seen that picture before many times, you know, what a neural network looks like. Again, it has its own gray matter. These are the neurons. It has its own white matter. These are the connections between the neurons. It is organized, those neurons are organized in layers. That's not the case in our brain. We have the input layer, we have the output layer, and in between we have those magical deep layers, which are the famous transformer blocks, like the attention blocks. The neurons are basically mathematical formulas, and they contain numbers. Those numbers are called biases. These are not the kind of bias that we mean when we say gender bias, racial bias. Bias here is just a number, it's a statistical thingy, right? The connections have their own numbers, and those are called weights. And those biases in the neurons and the weights in the connections are the so-called trainable parameters. So training is all about setting those numbers right. And once we have trained the model, we have all the little numbers. So as you can see here on this model, we have already little numbers in our neurons. These are the bias values, and the connections are of different weight, of different thickness. So these are different numbers. Let's say the thicker the connection, the higher the number. I just couldn't put in all the numbers there. So what happens here is that we have a giant computational network operating with numbers, but language is not numbers, language is words. So what we need to do is to convert those words into numbers. And that's what the very first layer of the neural network does. Its job is to take words, technically speaking tokens, but I'm be calling them words, okay, just because it's easier to tell the story. So it takes the words and turns them into numbers. Then those are processed through the deep layers, and that at the end of the network, what we have is the last layer, and that layer produces logits. And these are again simply numbers. It's a fancy, logit is a fancy word for a number that comes out of a neural model. How do we turn words into numbers? Well, you probably know about word embeddings. The idea here is that you can map words onto a multidimensional kind of semantic coordinate structure, coordinate space, and assign to them coordinates, and coordinates are in fact numbers. So if we have a sentence such as today the sky is blue and bright, then we can say, well, today is a point in this coordinate system, in this space, which corresponds to 5 on the x-axis, -2 on the y-axis, and 3 on the z-axis. The interesting thing here is that this kind of mapping of words onto semantic space and assigning coordinates, which are called embeddings or word vectors, right? They tend to cluster. So the result is that words that are similar cluster together. They are positioned in the same kind of area of this semantic space. So if today is here, then tomorrow, the word for tomorrow will be positioned somewhere there. If sky is here with these embeddings, these coordinates, then air is gonna be somewhere close by. If bright is here, then clear or light is probably gonna be here. And all of those words have their coordinate systems in this three-dimensional semantic space. Perhaps a better way to actually explain it is if you look at the RGB color cube, right here you have 3 dimensions. You have the dimensions of greenness. It encodes degree of greenness, the dimension of redness, and the dimension of blueness. And then when you create composite colors, you actually give them the coordinates, right? You say this kind of red, you are gonna find it if you move 230 positions to the left or right on the redness axis, and then you don't move on the greenness axis, and you go up like, or you move 84 positions on the blueness axis. That's where you find that color. And I think this is a very good way to actually explain semantic space, especially multidimensional semantic space, because look at this animation, right? You have these 3 axes, they are perpendicular to each other, okay? And now we can kind of change, we can move along this axis, so we can move along the redness axis, right? And we get like from no red to red. Here we move from no blue to maximum blue. But something even more interesting happens in this semantic space of colors. If we move like randomly and we kind of position, you know, the object, the ball, different places, you see that something interesting happened with it. It became lighter. It is lighter. It was white. When we go back, it actually becomes black, darker. So here we are actually dealing with 4 dimensions. 4 dimensions. We have the dimension of green, the dimension of red, and the dimension of blue. But we have this additional dimension of light versus dark, which is actually, we can think of it as being perpendicular to the other 3 dimensions, but this is something that we cannot imagine anymore because our brain is not made to imagine more than 3 dimensions. We can imagine 1 dimension, that's a line, 2 dimensions, that's a plane or a square. This is the world of a bacteria. A bacteria lives in a 2-dimensional space. It is so small that the 3rd dimension, the vertical one going up, doesn't matter. So for a bacteria, 3 dimensions is something that a bacteria cannot imagine. Okay, we live in a 3-dimensional world and we know how that looks. Some people claim that they can see, I cannot, but they claim they can see 4-dimensional objects. A 4-dimensional cube is called tesseract and it's drawn like this. I cannot parse it, right? But that's where we end. And in a large language model, the semantic space has at least 300 dimensions, totally beyond our imagination. This is what the word sky actually looks in this system. These are the first 100 dimensions of the embedding for sky. And I left out the remaining 200 because you wouldn't see the sky if I put all the numbers there. Okay, so Now that we know how words are turned into numbers, what happens then? Well, then comes the most exciting part of neural networks, and that is the transformer blocks, the middle layers inside which the attention mechanisms reside. And the attention mechanism is this innovation that I told you changed the world, in my opinion. Let's see what happens there in these attention mechanisms. So this attention basically allows the model to look at the entire text at once and mathematically weigh the importance of every single word in the text relative to every other word in the text. So it decides, basically the model decides which words matter most for which other words. So for example, you can see here that the word blue is kind of connected with a thicker line to the word sky and to the word air and to the word fresh, but not so much to today, okay? Because sky is more important for the meaning of blue. This is why we know that blue here means a color, and it doesn't mean the emotional state of being sad, because blue is actually an ambiguous word. It can mean either sad or blue. So how does the model know that blue here means color? Well, we have the word vector for blue, right? We know where blue is in the semantic space of the embedding. And then through the attention mechanism, we generate another vector, the so-called attention vector. And when we add the attention vector to the word vector, we shift the meaning. So if the attention vector is generated in the context of sky and air and so on, then we shift the meaning of blue to mean the color. And if this word appeared in a different context about feelings and emotions, then it will have a different attention vector, and it's going to shift its meanings towards, being sad. So like physically, you can imagine it again with this multidimensional semantic space. Imagine this is the area where all the color words or the color concepts are located, and this is the area for emotions. So when blue appears in the context of sky, the attention vector literally drags the word vector towards this area. So it means blue. And if it appears in the context of feelings, then the other attention vector will literally drag the word for blue into the emotion area. Okay, that's how disambiguation works. Okay, so now we know already that at the first layer, the LLM converts words into embeddings numbers. Then this goes through the transformer blocks, which enrich the meaning by absorbing the context. And actually, as we move through the network, we increase the abstraction. The network processes more and more complex things, and at the end we output the final number, right? So at the level of an individual neuron, what happens is that this neuron gets all the numbers from the previous neuron, from the neurons in the previous layer, does a mathematical operation there, and passes on the signal to the next layer. The mathematical operation is super simple. It basically just takes the number that comes from the previous neuron, multiplies it by the weight of the connection, and sums it up with its own bias, and then applies an activation function to know whether to pass the signal onwards or not. That's it. Super simple math. Okay, so what in the end LLMs do are predict the next word in a sequence. So if we have an input such as the sky is blue, and what we expect is that we will get a word like bright. But in fact, LLMs do not predict a single word. What they do is they predict the probabilities for all the words in the vocabulary to appear as the next word. So the last layer actually contains exactly as many neurons as there are words in the vocabulary. And for each one of those, you get a number, and that number is converted to a probability that that word is going to be the next word to follow. So they're basically simply giant calculators of conditional probabilities. Okay, and when they predict that next word, they do it one at a time. So if you input a sentence such as the sky is blue and the LLM needs to continue that sentence, then it will say generate bright, and then it will pass back to the beginning of the network, this whole new sequence now with bright appended, and generate the next token, the sky is blue and bright with And now it's going to pass this again and say the sky is blue and bright with soft, and then again with soft clouds, white, suppose white, and then again with soft white clouds, and so on, one at a time. One at a time. And this is called autoregressive generation because the whole sequence goes back to the beginning and the next token is generated again, and so on and so forth. So a little bit more math. What happens at the end? As I said in the last layer, we have numbers, logits. So every neuron there corresponds to a word and it gets a number. And what do we do with that number, right? A number is not a word. So we need to do some things. First thing that is happening is we apply the so-called softmax function, which takes that number, which you can see here, for example, 0.82, and converts it into a probability, so that what we get there is something like, oh, there is a 35% chance that clear is the next word, and a 44% chance that bright is the next words. But how do you turn words into numbers into probabilities? That is super simple. So I really want to show you how that is done. Suppose you have a neural network with just 3 nodes at the end, right? One for the word cloudy, one for clear, one for bright. And these are the numbers that came out of this giant calculation that happened. Cloudy gets number 0, clear gets number 1, and bright gets number 2. What we do now is we take a very special number called Euler's number. Doesn't matter what it is, you just know it is 2.71. And we exponentiate it to the number of the words. So we say, okay, for cloudy, we take this Euler number, we put it to the power of 0, which is 1. To the power of 1 for clear is 2.71. And Euler number to the power of 2 is 2.71 times 2.71, which is 7.38. Now we sum all of these numbers together and we get 11.1. And then what we do is for every word, we actually divide its resulting Euler number exponentiation by the sum of all the results. So we get 1 divided by 11.1, 2.71 divided by 11.1, 7.38 divided by 11.1. And this gives us 0.1, 0.25, and 0.65. And these are already probabilities. This you can rewrite as 10%, 25%, 65%. This is how we know that there is a 10% chance probability that the next word in that sequence is gonna be cloudy, 25% that it's going to be clear, and 65% that it's going to be bright. So the whole point of training is that the model sets the parameter number so that these logits at the end are converted through softmax into those probabilities that actually match the statistical distribution in the data itself. That's it. So now what we have is we have the final layer output numbers, a number for every word in the vocabulary. We converted those numbers into probabilities. What is the chance that this is going to be the next word in that sequence? But now the question is, how do we convert probabilities into like real things? Like, how do we actually choose? And this happens through the so-called multinomial distribution or multinomial sampling, which actually samples the next word proportionate to its probability. This means that if we run that prompt 100 times through an LLM, in 44 times out of those 100, it's gonna give us the word bright. In 35 cases out of those 100, it's gonna give us the word clear. And that's it. But now the question is, I'm gonna run this prompt just once. So what does it mean 44 times out of 100 I'm going to get bright, given that I'm sending this translation just once, right? How does the model know that it needs to select bright? It's a little bit like when you have, presidential election and somebody tells you this president has a 65% chance, like this candidate has a 65% chance to be the next president. What does it mean? If we run this election 100 times, this candidate's gonna win it 65 times out of 100. Nobody runs an election 100 times with the same candidates and setup. So here is how this gets solved very beautifully mathematically in a large language model. Now remember that what we have is, from the softmax function, we have the probability value for every word, for every token. Now we are going to do a very simple mathematical trick. We're going to take a sequence of 100 numbers from 0 to 99. Right? Like programmers like to start counting from 0. They don't count 1, 2, 3. They count 0, 1, 2. Okay. So we take an interval containing from 0 to 99, and we start assigning an interval to every word that contains the matching count of numbers. So we say clear, you get an interval assigned from 0 to 34. This interval contains 35 numbers, 0, 1, 2, 3, 4, 5, up to 34. That's 35 numbers. For the, we assign an interval which contains the next 5 numbers, 35 to 39. That's 5 numbers, 35, 36, 37, 38, 39. Okay, 5 numbers. For jelly, just one number in the interval because it has just 1% probability. For bright, interval for 41 to 84, and so on. So we take 100 numbers and we basically assign them in portions to the probabilities of every word. And then the magic happens. Then we roll the multinomial dice. It's basically a random number selection function. Imagine a dice with 100 sides. On each side, you have a number from 0, 1, 2, 3, up to 99. You roll it and you get 67. And now you need to pick the word in whose interval this number is contained. Which word are you gonna pick, or is the model gonna pick, if the multinomial dice rolls and falls on 67? Do we have the chat open? Let me see. Who's gonna type for me in the chat? In the chat, let me see. Bright, exactly. Okay, keep typing. What about if we roll it and we get 21? Which word is gonna come out from the model? Clear, exactly. 50 gives us bright. 80 gives us, what does 80 give us? Bright. 48 gives us bright again. 99 gives us big. The sky is blue and big. Yeah, it doesn't sound bad. This is why we actually get hallucinations, because you see that if the multinomial dice falls on 89, we are going to get ouch, and it doesn't make any sense, right? But we are going to get ouch, right? So this is how the selection works. We roll the multinomial dice, and because bright has such a large interval, there is a very big chance that this randomly generated number is going to be contained in the interval between 41 and 84. So that's how AI selects its next word. It simply rolls a multinomial dice. And at each step, as it does it, it calculates probabilities, picks one word among the many possible ones, and then another, and then another, and then another. There are no feelings. There is no beating heart. There are no waving hands. It's just a probability distribution. But from this randomness and from this probability distribution, something that looks like creativity emerges. Because in LLM, the creativity comes from this controlled randomness. But in humans, the creativity comes from our embodied cognition, from our grounding, right? But LLMs still sometimes surprise us, right? Because this randomness allows for variation, and variation allows for surprise, and surprise sometimes feels like creativity. But that's the magic. It's just the multinomial dice rolling. It's pure math. It's pure math. So I actually tend to say that LLMs are just pure math without the experience, and translators are all experience but without the math. So I hope you don't mind that I push so much math on you today. Yeah, but that's the reason why translation is actually profoundly human, because it's not like just choosing the next word, right? It is physically re-experiencing the message and passing it further. But yet with AI, I feel have started doubting a little bit the role of the human translator, because, AI can very perfectly mimic language and mimic translation, and it moves very fast, and it feels a bit destabilizing, and it feels like this change is just coming upon us too fast. And as human beings, we are naturally resistant to change, and this is understandable. And whenever I start thinking about that, I always remember the words of the father of one of my friends at university, who was an ornithologist, and he once told me that there is this very interesting phenomenon in migratory birds, birds that migrate for the winter. And that is when a population, in a population of migratory birds, every winter, there is a small percentage, like it varies between 2 and 5% of the birds that don't choose the good old route for their winter destination. They choose a different path. They deviate, they explore. Sometimes they perish, but sometimes they find a better winter destination, a better place to spend the winter. And then the winter after, they're joined by more birds of the main flock. And then gradually the entire flock joins those split migration 5% of birds. And I think that change in any species starts with those 5%. And I wish you that at the next step, you find many such new ways to reach new destinations with new means and new tools that we have. So you are going to hear soon what the next step is going to be about. So I won't delay that anymore. I just want to wish you to be adventurous, be open, be one of those birds that take the split migration path, because innovation, you know, it gives us the tool, but it's our creativity that gives those tools the direction. Thank you very much. Thanks for having me.
Thank you so much, Marina. That was really fascinating. I feel actually a bit emotional after this, and I'm sure I'm not the only one. And there are so many things to pick from this. You know, dancing with words. Is that your next book? I don't know. And to really understand how we are Stone Age human beings function in that in this new world. And I don't know if you can see, well, now you can see all the reactions you've received, so many little hearts popping up, and also these other reactions. So absolutely fantastic. Let's move to the questions and answers and see what we have there. Armando asks, how does the role of the left and right brain operate on this? You're not a neuroscientist, but
let me see at what time the question came in, because
it was early, yes, when we were still on the
I
brain.
suppose that here we were talking about the Wernicke area and the Broca area and so on. So you know, the language processing has always traditionally been thought to happen in the left hemisphere, right? The Wernicke here, when you scratch yourself behind your left ear, that's the area you're scratching, right? But as I showed, and as recent neuro scientific research shows, language engages the entire brain, including your motor cortex and your emotional cortex and your sensory cortex, everything. So language is a full brain activity. However, there are some parts of the brain in the left hemisphere which are specialized in language. So if you get a damage of your Wernicke's area, you don't understand language, but you can produce fluent language. If you get a damage on your Broca area, you actually understand language, but you cannot produce language. So while damage to other parts of the area of the brain, say on the right side, are not gonna impede language understanding and production so much, they are still very important for the full experience of language, and especially for translators.
Okay, thank you very much. And there's a connected question about if the connections are different for translators and interpreters.
Yes, I haven't seen research about how the brains of translators and interpreters are different. There is research showing how the brain of translators and interpreters, like professionals and just pure bilinguals, are different. So speaking two languages and being bilingual actually is not this, you don't have the same brain as the translator's brain. A professional translator has really way more gray matter in the parts of the brain that are dedicated to language, and much more white matter as well. Even, you know, fascinating, you know, there is this corpus callosum. It's a very thick bundle of fibers that connects the right hemisphere with the left hemisphere. In translators, it is thicker. than in non-translators. So the connection between the two hemispheres in translators is thicker, but the exact difference between interpreters and translators, I wouldn't be able to answer. I can only I can only guess that for interpreters, the long-term memory is probably trained, the short-term memory, sorry, is probably much more better trained because they need to retain the source meaning in their working memory as they produce the target language.
Thank you. I think we'll jump a little bit. I'll come back to some questions higher up, but I would like to pick the question from Sarah Palmer. Fantastic talk.
Thank you, Sarah.
You made the differences between how humans and LLMs translate inspiringly clear, embodied experience versus probabilistic prediction. Sarah's question is about industry translation workflows that integrate the two ways of translating, like post-editing. How do you think post-editing impacts the processes in translators' brains? Is embodied experience somehow blocked by the probabilistic calculated output provided? Are there other human-machine interaction options that might work better to support human embodied knowledge in translation?
That's an excellent question. I wish I had a good answer to that, meaning an advice how to go forward with this human-machine interaction. One thing I can answer, and that is known, is that the brain activation during post-editing is different than the brain activation during, let's say, interpreting in a room without any tools. So tools do change the way our brain reacts and processes information during translation. Post-editing and translation, to me, are two completely different like in nature different activities, because post-editing works primarily on the target language and you're polishing the target language, whereas translation by necessity first goes through the source language. It's not just a reference, it is actually the source. You know, you need to understand the meaning. My guess is that this also impacts the embodied cognition, which must be much weaker with post-editing than when we translate out of the source text directly. Because editing as an activity is different. It's not the creation of the text, it's the modification of a text. And I think this also impacts the quality of the outputs. That is a text that has been translated from scratch with all the experience and the embodied cognition and the grounding and so on will feel different than a post-editing text where the source will inevitably shine through. There will be this spillover effect from the source. However, how to shape our industry in a way that machines do not, we get the best out of the machines and the best out of the humans. I'm still trying to work my head around it, honestly, not just me, everybody, because let's agree on that. I'm a tech person, actually, so I'm all about tools, and I think that tools have their place. Like a human translator, because of the cognitive load, gets tired after a couple of hours, starts making mistakes, needs a coffee break, needs a bio break, needs to sleep, needs to eat. An LLM doesn't need that at all. So the scale and the massive volumes that tools can help us process, that's something that we cannot ignore, and we should leverage from that. But the key here is to find a smart way to use the tools in a way that they help us produce better quality, better output, and not the other way around. And keep the value of the humans. And I'm sorry I don't have the answer for that. I hope I will find it one day, but at this moment, we are still trying, exploring, searching.
It sounds like the topic of a next talk, actually, Sarah's question there. So I want to go back to Vanita, who has actually several questions, but maybe the last bit of the question we could start with, how we can judge the AI tools, whether how do you measure the tools?
How do you measure the output of
I
the
think
tools?
that is what is meant by the question, yeah.
Well, my opinion has always been that the way in which a text was produced shouldn't have impact on the way its quality is evaluated. After all, when we evaluate the quality of the text, we are interested in how the reader, the end user, the consumer of the text will experience it. We don't care who created it, whether it's AI, machine translation, or a sequence of three humans, one created the draft translation, the other one proofread, and the third one edited. I don't think we should be changing the way we evaluate the output based on who produced it. That seems unfair to me.
Okay, thank you. And Christina, she comes back to the question about should we change what I remember a couple of years ago at TEF we had this long discussion whether we should call human translators something else, but Christina suggests why don't we call the LLMs, the AI translation, something else. I don't know
Yes.
if you have a comment to text emulation.
Well, I think AI translation is kind of a easy shortcut. After all, language allows us to create this metaphors, comparisons, and shortcuts. So for me, it's a valid term to call translation, AI translation, because after all, it's converting. The result is that you have a conversion from a source text into a target text, even though the process behind it was very different. The result is, yeah, you had something in Spanish, now you have it in German. So it was a translation. But the process indeed is, I wouldn't even say text emulation. It's, let me see. Yeah, maybe text emulation is a good term. Generation, it's a statistical, it's a mimicking statistical patterns in training data. That is what it is. Yeah.
Yeah. And then we have Antonella who is asking whether LLMs are trained for translation. I mean, that's yes.
Large language models actually were never trained for translation. Translation was the so-called emergent capability. Emergent capability is when you create a tool to do A, and then it turns out that there's a side effect. It also has the skills to do B. Okay, this is an emergent skill in a tool, in a system. So LLMs were never trained for translation, and it was a bit of a surprise that they're so good at it. But they can translate. They can translate because they are trained on multilingual data, and that's the topic of another talk. Yeah, but neural machine networks, which are encoder decoder systems, are trained for translation, but large language models are decoder only, and they weren't trained for translation per se
Okay.
specifically.
Thank you. I think you have a topic of yet another talk from
Yes.
Min Yu. Could you elaborate further on the implications of the absence of grounding and embodiment in AI models?
We've seen it many times. It has a name. It's called hallucination. The implication of the absence of grounding in the real world is that models hallucinate. That's the main symptom. But there is one more, and that is bias as well. Bias is also one of the implication of absence of grounding. And you, Min Lin, are working on bias. I know that. So that is a topic for you.
Yeah, well, we have an example from Helena Lopez, who translated the title of the book Eve, How the Female Body Driven 200 Million Years of Human Evolution with AI, and it
Oh my
translated Eve
goodness.
into Portuguese as Véspera, like Christmas Eve instead of Eva. Yes, so that's almost like a comment to what you just said.
Yes.
We'll fit in another question from Ildiko. How do you think experienced specialized translators and terminologists can navigate this quite chaotic landscape with AI hype? I'm sure we'll have to have legislation to ban the use of AI in high-risk translations. Until then, I'm sure we have to communicate this fit for purpose principle and that it is not enough that the translation has English words in it. I am convinced that inaccurate translations will lead to legal disputes and damage the reputations of multiple companies. And I think that links to the earlier comment we had as where is the place for linguists or for
Absolutely.
translators.
And this actually links very well to to the next TEF. I won't give a spoiler, but here is what I think, Ildiko. I think that your role has never been more important. I am a linguist by education. I work with AI and tools and technology all the time, and I can see how many decisions need to be made by linguists and how many inexplicable AI behaviors can actually be explained by a linguist who understands how language works. And it is your role now, it is your task to actually de-hype and to bring in the linguistic expertise, which it's hard to have a voice, right? We need to be louder, but we need to bring in the linguistic expertise and manage the risk and also explain the problems, illustrate them, and tell the story. I'm going to end up actually with a quiz for you, not a quiz, but something for you to think about. You can then write to me on LinkedIn or maybe here in the chat. Here is a problem that we encountered with AI that couldn't be explained by anyone but a linguist. And here is what we did. We are using AI at RWS to manipulate translation memory. Sometimes we need to convert millions of words, say from informal text to formal text. So a text written, let's say with do and to, the informal pronoun, to formal text because the client decided to start speaking more formally, or the other way around, from formal to informal. LLM can do that perfectly well in one direction and cannot do it in the other direction. And the question was, if LLM can do that task perfectly well with high accuracy in one direction, why can't it do the same thing in the other direction? And the answer is anchored in language. And you, as a linguist, please think about it. Come back to me and tell me, first of all, in which direction can the AI do this? In which direction does it fail? And then tell me why. So that's my homework for you.
Thank you very much, Marina. I think you've given many of us also the tools so that we can explain the value of the human translator.